Right, so welcome everybody. So let me share my screen. Okay. Okay, then let's start. So we are discussing Gröbner basis. So the topic is Gröbner basis. Okay. So computational ideal theory. So we have a polynomial ring over a field. We want to study ideals, and the focus is now on algorithmic questions. So how can we decide anything about these ideals? And the crucial concept is the one of Gröbner basis. So let me recall it. So I assume I have an ideal in my polynomial ring over a field. An ideal. Then we had this concept of the leading ideal. Leading ideal. Sometimes people call it initial ideal. So it has several names. So I call it leading ideal. Leitideal in German. And it's the following. I denote it this way. So take any element f in the ideal, which is non-zero. Okay. Then it has a leading term, LT of f. And then we look at the monomial ideal generated by these leading terms. So that's the leading ideal. The monomial ideal generated by all the leading terms of polynomials in the ideal. Okay. Right. And the Gröbner basis, what is a Gröbner basis? A definition. So a collection of polynomials. Actually, these polynomials have to be in the ideal. This is called the Gröbner basis. So for short, I just tried G basis. Okay, it's just shorter. This is Gröbner basis. If the following holds. Well, I look at the ideal generated by the leading terms of all these GI. Okay, so this generates a monomial ideal. And clearly, this monomial ideal is contained in the leading ideal. But I'd want it to be the leading ideal. And if this is the case, then I call G a Gröbner basis. And this is not definition, this is a statement. So this is the definition. Okay. So clearly, this is a conceptual definition. It's not a computational definition. It's not clear how we would want to test, okay, whether such a G is a Gröbner basis. Well, we will see how to do that later. For the moment, it's just a definition. Okay, and so what we showed, a couple of things. So we showed that G always generates the ideal, generates ideal I. Okay. We also showed that every ideal has a Gröbner basis. Every ideal I has a Gröbner basis. And this is already very interesting because Gröbner bases are finite set. So in particular, this implies that every ideal in a polynomial ring is finitely generated. Okay, and thus I is finitely generated. So this is usually expressed by saying that the polynomial ring is Noetherian, means polynomial ring is Noetherian ring. Noetherian ring. So this concept of Noetherian I will discuss later in detail, but for the moment, yeah, I just mentioned, is named after Emmy Noether, okay? Pioneer in abstract algebra. Right. So what else? We had the reduction notion. Okay, let me also recall that briefly, but not in every detail. We had the reduction notion. So, okay. So what we want to do, kind of, we start with F, and then, okay, I defined what is a reduction, a one-step reduction, okay? And I can do this many times. So what was this one-step reduction? So right, what do I do? Okay, I pick one of the elements of G, let's say GI. Look at its leading term, the leading term of GI. And then I try to see whether one of the terms of F is divisible by the leading term of GI. And if yes, then I can subtract from F a suitable multiple of GI in order to kill the corresponding term. So this was roughly the definition. And if we consecutively apply such one-step reductions, we get a many-step reduction, which I denoted this way, okay? And when I arrive at a polynomial H where no more reduction is possible, then I call it a normal form modulo G. Okay, so H normal form modulo G. That's also an important notion, so let me underline it. Okay. Okay, but when defining this reduction notion, there is some arbitrariness because it's not an algorithm, as I said. But if we define the order in which to do things, so for instance, we say that the G has G1, G2, G3, and I have to work on them in that order. Also, when I try to kill terms, I go in this. Okay, there's something very important that I didn't say, but it's obvious. I mean, the notion of Grabner basis only makes sense with respect to a term order. So maybe I should have said this, fix a term order. Of course, otherwise it's not defined what it means to have a leading term. So a term order is fixed. So, okay, so I define, so to say, the order of operation, I get a division algorithm. And then, right, and then I also had a symbol for that. Okay, for instance, I could take for H the remainder of the division of F by G. So I denoted this way. Remainder of division algorithm. Okay, but here this is only defined when G is ordered. So need G ordered. Okay, but then once it is defined, once G is ordered, then it's a well-defined thing. Okay, so more or less this was the repetition. Are there any questions? Comments? Examples will come, so you have to be a little bit patient. Okay, doesn't seem to be the case. Then let's go on. So, right, so a proposition. We will see Grabner bases have many nice properties. So, okay, before writing the proposition, maybe I remember something. Okay, so if maybe this, no, I do it this way. I can use my technology, move this down. So then, so if F reduces to H, I can always write, I can decompose. F is G plus H, and G is in the ideal. Okay, this is always possible. I hope you remember. Right. When you reduce, you stay in the congruence class of the ideal. Okay. Right. And the nice thing is now, so this is true for any division, by division by any set of polynomials. But what is nice now, if I divide by a Gröbner basis, this normal form, or this whole decomposition, is unique. So this is the contents of the next proposition. Okay, let G be a Gröbner basis. Let's say G1 up to GS be a Gröbner basis of the ideal I, and F a polynomial. Okay, sometimes I just write X, but I mean I write X, I mean X1 up to Xn. Just want to save a little bit of notation. Then there is a unique decomposition. Okay, F equals G plus H, where G is in the ideal and H is a normal form of G, H normal form. Okay. And I can also say H, I can actually compute H, moreover. Okay, not readable. H is the remainder of the division by G. H is remainder of division of F by these polynomials. And what is now remarkable, because of the uniqueness property, the order is irrelevant. So here, the essential unique, right? Thus, remainder independent of order of these polynomials. So somehow the deficiency we had here in this division with remainder does not exist anymore when you divide by a Gröbner basis. So everything is good when you have a Gröbner basis. Okay, so let's prove this. Proof. So first, existence. So the existence is, by what I recalled, actually is, I hope is now clear, because I already said, well, okay, let me recall it. What do we do? I have F. Then I reduce, okay, until I reach a normal form. So this is always possible by this well-orderedness, okay? There can be no infinitely strictly descending chain of polynomials. We proved that. So for that reason, we can have such a representation. So the existence is, okay, I say clear now. Okay. And the interesting part is the uniqueness. Okay, uniqueness. Uniqueness. So let's assume I have two decompositions. So F equals, say, G1 plus H1 equals G2 plus H2. I have two decompositions. My GI are in the ideal, and the HI are normal forms. HI, normal form, mod G. Okay. I want to show, okay, yeah, it's clear what I want to show. So first of all, okay, we have to remember, what does it mean, normal form? It means I cannot further reduce. But concretely, this means the following. So T of HI was the set of terms of HI, the set of terms, and being a normal form means the set of terms of hi is disjoint of the, okay, how do I write it? Okay, let me write it this way, so it will be general. So this notation here, okay, this is just my shorthand for the monomial ideal generated by the leading terms of G1 up to GS, okay? So actually, and this is the leading ideal because we have a Grabner basis, okay? Right. So this condition exactly guarantees that I cannot reduce further my HI. So we had this, okay? So I have this. This I have, okay, so it's clear, okay? I continue here. Right. Or maybe I don't have to write this. Okay, right. So let's assume if H1 is different from H2. So then I will arrive at a contradiction at some point. Then, okay. So H1 minus H2 is G1 minus G2 minus G1. This is in the ideal. So I have a non-zero element in the ideal, and I can look at its leading term, okay? The leading term of H1 minus H2, okay, sorry. Yeah, this is in the initial ideal. Okay, because it's the leading term of an element, a non-zero element in the ideal, right? But I know this is my assumption that I deal here with the Grabner basis. I know the leading ideal is generated by the leading terms of the GI. Okay, good. But then you see where the leading term of H1 minus H2, what is it? It must be a term of H1 or of H2, but this is contained in the union of the term set of H1 and H2. Okay. Now I have a contradiction. I have a contradiction to, maybe let's put here a star, to star. Because star says the term set of H1 and the term set of H2, they are both disjoint to that. Okay, so this cannot be. Okay. So this is the proof. Okay. Is there a question or?
I think you mean this is an element of instead of a subset.
You're right. Thank you. Thank you. Thank you. Thank you. That's what I wanted to say exactly. Good. I'm very glad you correct me because then I know I'm not speaking out into nothing. I always enjoy feedback. Okay, so I proved the proposition. Some corollary. Okay. I can now I'm in a position to decide whether the so-called ideal membership problem. So assuming I have a Grabner basis, let G be a Grabner basis of I. And I have any polynomial. Okay. Assume I want to find out whether F lies in the ideal. Okay. From the definition, it's not clear how to do this computationally, but now we can say this is the case if and only if, well, I just do the division with remainder. Okay, I divide. This is the remainder, is well defined. Okay, if G is a set, but we just learned the order of G is irrelevant. So this is in I if and only if this remainder is 0. Okay, this is because, let's go up. Let's look at the proposition. My F, well, those F that are in the ideal, they have the decomposition F equals F plus 0. Okay. So that's a decomposition, a valid decomposition. 0 is always a normal form. Right. So I just have to check whether this H here, which is uniquely determined and can be computed with the distribution algorithm, I just have to check whether this is 0. So this solves the ideal membership problem. So hence, okay. Okay, so I don't know, in the 1920s, I think, people were thinking, right, people were thinking about decidability. So after Gödel came up with his incompleteness theorem, people, I mean, in the area of mathematical logic, it has grown a lot, and people were thinking which questions actually are decidable, okay? And there was this question, whether the ideal membership is decidable or not. Let's assume we have the field of rational numbers to be concrete, okay? And then Emmy Noether, she had a student, Grete Hermann, and she answered that in her PhD thesis, okay? And she showed, she not only showed that this is decidable, she even proved some bounds, okay? But we are not discussing the bounds here, but I can say the ideal membership problem for polynomial ideals is decidable. Okay, so, okay, means there is an algorithm for it. Okay, this may look like a very weak statement, and I agree, it is quite weak, okay, because we don't know, we have no idea how fast this is algorithm, okay, but okay, there are some other problems in mathematics that are undecidable. And do you know, have you ever heard about that? Or nowadays people only learn that in connection when they study computer science. So who has heard about undecidability?
So there is, for instance, in group representation where you have the generators and the relators, that showing that two are the same is undecidable.
Correct. Very good. Exactly what I wanted to say. Right. The corresponding problem in the non-commutative world, you talk about groups, or you can be more general. You talk about monoids. Okay. There it's undecidable. Okay. But here we are like in a commutative world, and here it's decidable. So general often, okay, non-commutative setting, not decidable, commutative, decidable. Okay, right. Okay, so this is the interesting. Good. So now what I want to do, okay, I want to characterize Gröbner basis quite closely. Okay. So examples will come later. Examples will come later. If I have more theory, then it's easier to have examples, so then they don't have to compute. So characterization of Gröbner basis. So I have this theorem. I will characterize Gröbner basis by 4 equivalent properties. So I assume I have a finite set of non-zero polynomials. Finite. And equivalent or. Okay. So first, G is a Gröbner basis. Okay, I'm sorry, I have to. Okay. Going too fast. I also need to name my ideal. Okay, let I be the ideal generated by G. I hope it's clear. This means ideal generated by G and equivalent or. Okay, 1. G is a Gröbner basis of the ideal I. Okay. 2. Now this is what we know from the proposition. Every polynomial reduces to a unique normal form mod G. Every f in Kx reduces to a unique normal form So again, this unique is of course important because we always can reduce to a normal form. Okay. So actually, we learned that this actually characterizes Gröbner basis. Third property means for all f in I can reduce f to 0 or g in several steps. Okay. And okay, I have a last one. Maybe this is a little bit pedantic, but why not? Maybe it's not pedantic. For all f in I can say the remainder of the division of f by g is 0. Okay. So we just learn in the corollary that if I have a Gröbner basis, then this is the case. Okay. So this was this corollary. But the point is here, this is equivalent. This characterizes Gröbner basis. Okay. So let's prove this carefully. Proof. So I think I can start here. Proof. So from one
question.
Yes.
In the statement 4, doesn't the expression on the right depend on the ordering of G, or is it meant like for any ordering in G we have this?
Yeah. Okay. Good. You catch me. So I mean, yeah. I'm not. Actually, what I should say. Somehow I should order G. Otherwise, it doesn't make sense. I think the precise statement is this. Okay, you have your set and you order it anyway, somehow. Okay. And then this makes sense. Okay. And then if this is the case for you, this fixed ordering of the set, then you have a Gröbner basis. And the order is irrelevant. Okay. So I'm a little bit sloppy, but right. Okay. Yeah.
Okay.
Good. So from 1 to 2, that's what it was just a proposition. So we just proved that if you have a Gröbner basis, every element, every polynomial reduces to unique normal form. So now let's do the 2 to 3. This is a little bit subtle. Okay, maybe I can march. Okay, let's do this. Somehow we do this. Okay, I think it's a little bit subtle. It's interesting. How do we prove it? Actually, what I do here, it doesn't have a lot to do with polynomial ideals. It's just, these are general reasonings when you think about in a general algebraic context and you want to have a notion of reductions in normal forms, under which conditions you have unique normal forms. Okay, and there are general principles, and actually what I'm doing here applies in full generality, as you will notice from the proof. Okay, so what I do an inductive proof. Show, okay, first, okay, there are two parts, okay? Like show by induction on M, natural number, the following. So, okay, sorry, this I did not recall, but I will record it orally. We had another notion. We not only had the reduction, we had this one-step reduction, and then we looked at the equivalence relation generated by it. Okay, so this FMG, so what does it mean? It's like, let's say m equals 3. Okay, you make 3 steps. Okay, you end up with G. But in these steps, you can go forwards and backwards, mod G. It doesn't matter. Okay, in each, like, you're allowed to apply like inverse reduction. So this was the meaning of that. Okay, you can go forward and backward. That was the meaning. So this means what I have here means in m steps, I can go from F to G, but each step is going forward or backward, mod G. That was the meaning. Okay, and the statement is, if this is the case, if F and G are M equivalent mod G, there is an H such that, okay, F reduces to H mod G and G reduces to H mod G. So in a way, maybe I remove this. So I like to draw a picture, but maybe do it in color. Okay, orange is good. So I have F and G. Okay, so this is the situation, and then the point is I find an H. Okay, there is an H such that I can reduce both F and G to H mod G. Okay, so if 2 elements are equivalent, they have like a common reduction. Okay, that's what it means. And I'm going to prove it by induction on M. Okay, so the induction start is trivial. So let's assume M greater than 0. Okay, so then there are G1 and H1 such that. So I just resolve this M step reduction into 1 with M-1 steps. So I go from F to G1, and then there is another 1 step to G. Okay, this I can always, this is the definition of M step equivalence if you want. Okay, but now the good thing is here, now I apply induction hypothesis to that. Okay, I'm here and I find a common reduction. So okay, I just put it here. I find there is some H1 such that I can like complete this triangle if you want. Here is a star, here is a star, everything mod G. This is by induction hypothesis. Okay, maybe we have all these beautiful colors. So let's do it. So exists induction hypothesis. Okay. So then I have this picture. Now we will make a case distinction depending on what was this step. Did it go to the right, from the left to right, or from right to left? So let's assume now, if, let's say it was like that. I go from right to left. Okay, then choose H as H1. Okay. Because, okay, now the arrow, you see, the arrow goes here. So I can go this way and go down. And here I go down. So I've shown that that one, H1, is now my H, is a reduction of both of F and G. And I'm done. Okay, so so nothing happened actually so far. Okay, if the other case is more interesting. Okay, if G1 goes to G, and I should say G, I'll put this. Okay, then what I do? Okay, I need a little bit more space. I move this down. Maybe now color red. I like to work with the colors. So what do we do now? Well, I reduce H1 to a normal form. So I go to a normal form H prime. This is always possible. I can also reduce G to a normal form. I call it G prime, let's say. This is possible. But then, okay, you see, right. So I go from F down to this normal form. Or I go this way. But I now remember this arrow from G1 to G goes in this direction. So I go this way and then I go down. So I see G prime and H prime, they are both normal forms of F. Okay, because of the uniqueness assumption. Okay, in 2, I know they must be equal. Okay, so let me write a little bit something for those who do not attend the lecture, but just look at the notes. Okay, what do I have? Okay, let H1 reduced to H prime. I just write it again. G reduce to G prime, and H prime and G prime are normal forms. Mod G. Okay, then by the uniqueness assumption, okay, I must have H prime equals G prime. Okay, and then I have my triangle. So maybe I can, these things, they have to be equal. Okay, and I have, okay, I proved this. So maybe, yeah.
But why can you go from F to G1 in only one direction?
Sorry, can you repeat that?
Why can you go from F to G1? Because some of the arrows can also be in the other direction, I thought. If you want to go from F to G prime,
right.
you first have to go from F to G1.
Let me, right. Okay.
Couldn't one just start at G1
yeah,
and
right,
then
that's
do
right.
the same?
Correct, thank you. I did not explain it. I think nothing what I wrote was wrong, but I didn't explain it correctly. Sorry, because it's right, but I can show it. So because we can say we start at G. Yes. Okay, sorry. Yes, so let's go back. What was, everything is unique to, reduces to unique normal form. Right. But I know. Okay. So now let me think. I'm a bit confused now. Anybody sees the solution?
Yeah, I would start at G1 because from G1 we arrive at H prime and G prime via those reduction steps. And because it is unique for every polynomial, it has to be unique for G1.
That's right. So we ignore the F. We do this. We look at this part. That's okay. We look at this. So we go on the one hand this way. On the other hand, this is okay. And we go this way. Right. That's it. I didn't explain it properly. So maybe we can use another color. Violet is beautiful. We look at this part of the diagram. Okay. So uniqueness. So okay. See this part of diagram. I mean the violet part. Okay. So this statement, I think, is now proven. Show by induction on M, and now let's finish. Now, okay, now I can complete the argument. So now let F be in I. I want to show that I can reduce F to 0. Okay, by the lemma, by a lemma. Okay, I don't number the lemmas, which is maybe a little bit unfortunate, but I will explain what it means. By a lemma, we showed F is equivalent to 0 mod G. So we had this lemma saying that a polynomial lies in an ideal generated by G if and only if I have this. Okay, I hope you remember. Actually, that was the reason I reduced this equivalence relation. So, okay, so hence, by part 1, okay, which I just proved, there is an H, and F reduces to H mod G. And what would it be? 0 reduces to H. But the only way to reduce 0 is do nothing. H is 0. So then H must be 0. And I'm done. F reduces to 0. Okay. I hope the logic of the proof is clear. So the proof has like 2 parts. So maybe this part A. Now in part B. Okay. It's a bit tricky. And as you see also, I made a mistake while I explained it. So it also indicates that it's a little bit tricky. I said it's subtle. I knew it was subtle. Okay, but you helped me to solve it. Okay, but this is actually the remaining part is not hard. So we have to go on now. Let's now prove 3 to 4. I have all these beautiful colors. Now let's go to green. 3 to 4. 3 to 4. Okay. So again, I have to look 3 to 4. Right. We assume now every polynomial in the ideal reduces to 0. Sorry, I don't want to do that. I'm sorry. I do it this way. Sorry. Actually, I want to follow this direction first. So I first show the equivalence of 1, 2, and 3. The 4 I do at the end. So I assume every polynomial in the ideal reduces to 0, and I want to prove then G is a Gröbner basis. Okay. Oh, okay. Okay, so assume, so it will be indirect. Okay. Assume I have a non-zero F in the ideal, and the leading term of F is not in the monomial ideal generated by the elements of G. Okay, so this defining property of Gröbner basis is violated with the polynomial F. Okay, and then I take F minimal with this property. So this is, by the way, this is my standard trick here for proving things. I have my term order. This defines as this partial order on the monomials, and I can do induction. Okay, so you proceed this way. So F is minimal with this property. Okay, so but by assumption, okay, F is in the ideal, so I can reduce it to 0. Okay, this is my assumption, by assumption. Okay, and so, but now we see the problem. If you have such a reduction, let's look at the first step of the reduction. So there is some H, so there must be one step, okay? Okay, the step size cannot be 0 because F is not 0. So there must be at least one step. Okay. Remember, if you have the star, it would, okay, if F would be 0, this would be also okay, but we assume F is not 0. But now we see we have a contradiction, because then, when I have a reduction, then I know H is always less than F. Okay, in our ordering. Okay, and this contradicts the minimality of F. Contradicts minimality of F. So this part, this proof was, this direction was relatively easy. Okay. Okay, what else? Okay, so 1, 2, 3 were equivalent. Let's see. 1 goes to 4. Okay, I also have what was 1 to 4. Okay, I assume I have a Gröbner basis. This then, okay, division with remainder of any F in the ideal gives 0. This is by the corollary. By corollary. And 4 to 3 is clear. Okay, and this is proven. Okay, 4 to 3. If you want to see. Okay, if I have, of course, if I have this, then in particular I have this. Questions on that? So maybe I did more that one I had to do, but I like to analyze this concept in detail. Okay. Good. So no question. But the problem of course is if you want to really work with this concept, so many questions, how can we compute the Gröbner basis? But not even that, how can we test whether we have a Gröbner basis? Okay, so we need to find some criterion that is useful. Okay, and that's what I think Buchberger basically did. Okay, how to test? Okay, so we need criterion for testing that we have a Gröbner basis. So that's what we want. Okay, and where is the problem? Where is the problem? Let's go back to one simple example we already had, and there we see, okay, what is the problem? So, okay, what do we have? Like x squared plus y. I have two polynomials, x, y plus 1. Okay, this is my thing. And then this is not a Gröbner basis, not a Gröbner basis with respect to graded legs. So I always write it in a way so that the leading terms come first. So I want these two to be the leading terms. Because, more since, I can produce, okay, a canceling. So I can do the following. X plus y. I multiply with y. And then I subtract the second polynomial, which I multiply with x. Okay. And the point of all this is to write this. Where is it? You see, here I have yx squared, and here I also have yx squared, and it cancels. It disappears, this term, and what remains is this. Okay. And you see here the leading term of this here is y squared, and is pretty unrelated to the other leading terms that we had before. So, and y squared certainly is not in the ideal generated by the leading terms of this generator. So it's not in the ideal generated by x squared and xy. Okay. So we don't have a Gröbner basis. Okay. And the point was the term x squared y cancelled. Okay. Okay, and it may look like this is an arbitrary and trivial example, but actually this is the essence. It's all about this cancelling of terms, and somehow we have to control this, okay? And the way, how can you control this phenomenon? Kind of, you think of a way, how can I artificially produce cancelling? Okay, and then you prove that's essentially the most general way of doing it. Okay, it reminds me, like in cryptography, like poor TU is, okay, has been attacked. So how can you protect yourself against attack? You attack yourself. Okay, you company and say, attack me. Okay, and then you try to find where are the weaknesses and you try to defend you. Okay, it's in a way similar. So how, okay. So we have to master this cancelling of terms. Okay, notation. Okay, least common multiple, okay, of two terms or of two polynomials, I denote this way, is the least common multiple. Multiple. In German, KGV. Gleiches gemeinsames Vielfaches. So if we have terms, it's especially simple. LCM, say x to the alpha, x to the beta in our exponent notation. This is again a term, of course, x to the gamma, where gamma I is just the maximum of the natural numbers alpha I and beta I. Okay, so this is the... Okay, and now I introduce the so-called S polynomials. So that's an important definition. Okay, so let's assume I have two non-zero polynomials f and g. Okay, and then we look at the least common multiple of the terms, right? Denoted by t, like term. This is the least common multiple of the leading terms of f and g. Okay. So let me write down just this formula, and then I will explain you why it is there. Okay. Looks a little bit ugly, but it's very easy to explain what's happening. Okay, we call the S polynomial the following object. So we assign to f and g a polynomial, the S polynomial, and it's defined this way. So let me just write it. T divided by leading monomial of f times f minus t, now symmetric, divided by leading monomial of g times g. We call this the S polynomial. Of f and g. The f stands for CCG. Okay, whatever this is, it's called the S polynomial. S CCG. C. Okay, that's a difficult word. I believe it's the spelling is correct. CCG. I think it comes from Greek. Okay. I think I'm not 100% sure, but it means this. In German, it's called Joch. So that's what you put on the shoulders of the ox. So I believe this is the meaning of it, but I'm not 100% sure. It's a strange word, CCG. Okay. Okay, let me explain what's going on here. What we actually did, we enforced a canceling of a certain term. So illustration. Okay. So, okay, I write my f. It has a leading term times leading coefficient. So I like to write it this way. Here is the leading contribution and the rest is smaller in our order. I do the same with the G. Blah, 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 smaller terms. But now what I want to form a linear combination of these, of F and G, so that this contribution they kill each other, they destroy each other. So it's similar when you do Gauss elimination, you know, you want to produce a zero. Or you do, even if you do the division algebra, we also do such a thing. So how do we do that? So I multiply. Okay, I multiply with the term u. Okay, multiply with the term u, and also I don't like this leading coefficient, so I divide by the leading coefficient. So u will be a term. So this way, I make sure that the coefficient here will be 1. And here the same. I multiply with the term v. I divide by the leading coefficient of g. And then I subtract. So say we have this. T, I said T was the least common multiple of the terms, leading terms of F and G. Just repeat it. Let's call this is U times leading term of F or V times leading term of G. So U and V are just what I get when I divide T by leading term of F or leading term of G. Okay. So then you see, hopefully, I mean, what do I get when I do this? Okay. I multiply, I have this guy, I multiply with U. Then I get T. Okay, and this disappears because of that. Same here. This with this, I get T, this disappears. So if I subtract, I have canceling. So I see my S polynomial. Okay, maybe 0 times T if you want, and blah, blah, blah. So I have canceling. Okay, so this just explains why I make this definition. Okay, now if you check, that's exactly what I did. So this T over leading monomial of F is exactly right. T divided by the leading monomial is T divided by the leading term of F, and then you divide by the leading coefficient. Okay, and that's what it is. Exactly that. So there's nothing, formula looks a bit ugly, but there's nothing deep about it. Okay, now what is this good for? Right. Okay, next thing. Okay. Right, what I want to prove. So I want to prove the following. Let's say I have G1 up to GS. Okay, and I want to test that this is a Grabner basis. Then I will show the following. For each, you look at all the CCG polynomials. You pick any GI and GJ. So you look at all pairs, compute the S polynomial, And then you test whether they reduce to 0. And this you can do algorithmically. Okay, and the theorem will say I have a Gröbner basis if and only if this happens. Okay, this will be the statement. But in order to prove this, okay, I need some auxiliary lemma. So you have, let's be a little bit patient. Let me at least state this lemma and I prove it on Thursday. So, but this is crucial. But first, I think we have a, okay, note. In the example, just, okay, tiny little example I forgot to put. So I motivated everything with these polynomials, but indeed, what I want to say, tiny little example, the S polynomial of x squared plus y and xy plus 1 is indeed that. So, I mean, what I had at the very beginning, this example, okay, this is exactly what I analyzed now. Okay, I forgot to say that. Okay, and maybe it's also good to say the following. What is the S polynomial of two monomials? I have two monomials. From the S polynomial, what do I get? Okay. F and G are now monomials, and I compute the S polynomial.
Just 0?
0, yeah, because I mean, the S polynomial kills one term, but there is only one. If it's killed, it's gone, okay? So in a way, good. The S polynomial of two, I say of two monomials, I can say, vanishes. So if you, okay, if you just look at monomials, it would be completely uninteresting. Okay, and here is, I think, this is the canceling lemma. This, I believe, this is the crucial lemma. I like to call it canceling lemma. It's not hard. I mean, it's the proof will not be difficult, but I think it contains the crucial observation. Okay, it explains why the S polynomials are relevant. So we assume we are in a canceling situation. So I have the following. I have polynomials Gi. How do I say? So non-zero polynomials. Then I have terms. These are polynomials. Then let Ti. Okay, now I write it differently. This is not nice. Let me write it this way. G1 up to Gs. These are polynomials. Then I have terms. T1 up to Ts and T. These are terms. Okay, such that. Okay, so I look at Ti times Gi. So I have Gi and then I multiply with the term Ti. And the point is the leading terms of these expressions, they are all the same. They are all T. Okay, they are all T. Okay, and then I assume I'm in a canceling situation. Assume, okay, assume have coefficients lambda 1 up to lambda s in K, non-zero, okay, such that, okay, I formed a linear combination now, lambda I, Ti, Gi. I look at this. If you look at this, I mean, what would be the leading term? I mean, all of these have this T, okay, and there is this coefficient. Now I want to assume there is canceling. So I assume the leading term of this is strictly less than t. Okay, so canceling of t. Okay. Okay. Now if this happens, okay, the statement is, then I can rewrite, okay, I have this linear combination of the GI. The statement is, then I can rewrite this as a linear combination of the S polynomials of the GI. Okay. Then there are coefficients lambda JL in K such that, okay, how do I write it? Yes. Okay, it's a little bit technical, I know, but that's how it is. So I rewrite this as a linear combination over J and L. J, let's say J less than L. I have my coefficients lambda JL. And here I have certain multiples of my S polynomials. UJL I define in a second. Here I have the S polynomial of G, J, and GL, where UGL is T divided by the least common multiple of the leading terms of GJ and GL. So okay, you see what's happening. Okay, I replace this linear combination of the GI by the linear combination of the S polynomials. And how about this strange thing? So this is, sorry, I realized that, is it good? I'm just thinking. Yes, good. So this is a term, okay? So, okay. Now maybe I don't comment on it right now, but I will prove it later. Moreover, the leading terms of, that's actually what I wanted to say, of the UJL times this is less than T. So this is actually what we expect. So all these objects here have a leading term less than T. Okay. Okay. It's technical, I know. Okay. So let's do something with this lemma and prove this canceling lemma on first day. Okay, and let's apply it. Okay, let's apply it. Okay, so then we have the following nice theorem. So I have a collection of polynomials, capital G, consisting of G1 up to GS, non-zero polynomials. Okay, now equivalent conditions. Equivalent are 1, I have a Gröbner basis. G is a Gröbner basis of the ideal generated by G. Okay. And 2, now comes the useful criterion. For all pairs, for all I less than J, if I form the S polynomial of the generators, which I can do, it's a computation, and then I make division with remainder, okay, I divide by G. Actually, when I say this, I mean, you understand, in the order I have written of the G's, okay, I'm not too pedantic, this 0. Okay, so I mean, maybe I should write it otherwise ordered. Okay. Okay, and the third condition is saying for all I less than j, I can reduce the S polynomial to 0 mod g. Okay, I don't have to do it exactly in the way this algorithm does it. Okay, so these are equivalent. Okay, and of course it's useful. Okay, it gives a procedure to test whether I have a Gröbner basis. So, okay, I think I can do the proof if I hurry up a little bit. Okay, for 1 goes to 2. Okay, it's sufficient to note, I should have said this before, but I think it's pretty clear. The S polynomial is generated in the ideal, is lying in the ideal generated by J, because that's the S polynomial is a linear combination. Where is it again? Here, you see, it's a linear combination of F and G. So this is a linear combination of Gi and Gj, so it's here, okay? Right. So, and if I have a Gröbner basis, I know I can take any polynomial in the ideal. The remainder of the division will be 0. Okay, this we know. So this is okay. Okay, 2 to 3. This is clear. Okay, and the only work is here. 3 implies 1. So here we have to do something. So now I assume for all pairs ij, the S polynomial reduces to 0 mod g. And I want to prove I have a Gröbner basis. Okay, so let's take a polynomial f in the ideal generated by g, non-zero polynomial. I want to prove that, okay, what I want to prove? I want to prove the leading term of f lies in the monomial ideal generated by the elements of G. Okay, so let's write f as a linear combination of the G's. So we write it this way. The coefficient polynomial is ai, okay? And then I look what happens with the leading terms, right? Okay, put, let's say ti is the leading term of ai times gi. Okay, if this is non-zero, other sides, it's uninteresting. It's not there. Okay, then I note that, I mean, now I may have cancel. Maybe let's put here a star. I may have canceling or not, yeah. But for sure, I can say the leading term of f is less than or equal to the maximum of all the ti. Okay, taken over those I where ai is non-zero. Okay, so these ti, and when they are there, these are the terms. Okay, if there is no canceling, I have equality. Otherwise, I have canceling. So if equality, then there exists some I such that leading term of f equals ti. Okay, and the t, so, right. What do I want to write? Yeah, the lead ti, this is the leading term of ai times the leading term of gi. But then I'm happy. Okay, then I see the leading term of f indeed is in the ideal generated by the leading terms of these g's. Okay, that's what I want. Okay, then I see Gröbner basis. Okay, so, and what we have to do, we have to prove that this is always the case. And how can we do this? Of course, it will not always be the case, but if we choose our representation in a good way, then we can show this works. And I will choose the representation such that the t here, where is it, is minimal. What is the t? Okay, I have to define the t. Okay, this I denote t. Okay, and I choose such that t is minimal. Okay, and you want to show then, okay, want to show, okay, want to show that equality happens. Okay, and then I'm done. Okay. Equality. Here, of course, I want to show here is equality. So as usual, oh, well, let's assume we have, it's not the case, then let's lead it to contradiction. So assume, okay, argue indirectly. Okay, assume leading term of f is less than t. Okay. So now, so we will try to find a representation of f with, okay, with smaller terms, smaller leading terms, with the help of the S polynomial. So let me write again f. So first, I write that part of the linear combination where the ti, so the ti is the leading term of gi, where the ti is the maximal one, where the ti is the t. And then I have the remaining part, which is kind of uninteresting. Okay. Good. And now I split off here in that. Okay, I split off here the maximal parts. So I write it this way. Sum over all I where ti equals t. And instead of ai, I just put the leading monomial. Okay, and then I have to correct this. Here the coefficient is now ai minus the leading monomial of ai. Okay, and then plus this uninteresting part. Okay. So I want to call this, okay, how do I call it? F twiddle. Okay. So, right. So I assume leading term of f is less than t. So it means canceling happens. Okay. And the only way where canceling can happen is here. Okay. Canceling happens. So by assumption, I see that the leading term of, okay, f twiddle actually is less than t. Okay. But now we are in the situation of the canceling lemma. Okay, this is all about the canceling lemma. I have these GIs and I form a linear combination. Okay, and the coefficients are monomials and I have canceling. Okay, let's roll back to see this is the situation of the canceling lemma. Okay, I have these GIs. Okay, I form a linear combination where actually these coefficients are monomials. Okay, I have canceling. And then it says that this thing, which in our situation is now the F twiddle, will be a linear combination of the S polynomials. Okay. So the canceling lemma. Okay, implies there are coefficients lambda JL, and there are terms. These are terms such that I have twiddle. Okay, I think I need some more space. Let me produce. Okay, this I don't want. Okay, I have twiddle. Okay, I can rewrite, so maybe let me copy it first. So this I write as a linear combination of the S polynomials. I have the UJL and the S polynomials. Okay. Okay, also, I know from the lemma that these contributions here, all these things, they are less, the leading terms of these things are less than t. So leading term less than t. Okay, it's also part of the canceling lemma. Okay, but our assumption, well, we shouldn't forget our assumption. Our assumption is that the S polynomial is reduced to 0. Assumption gives all these S polynomials reduced to 0. Okay. Okay, so, but if they reduce to 0, now I can, right, they are in the ideal generated by the elements of G. So I can write them as linear combination of these G else. So it means there are some coefficient polynomials, B, okay, it's a lot of notation, B, J, L, M, I know, these are polynomials, such that, okay, the S polynomial can be written as a linear combination over M's, B, B, J, L, M, M goes from 1 to S, GM, okay? Now what I do, okay, this I plug in here, okay, to arrive at this desired contradiction. Okay, I should say, I forgot. I also know, sorry, I have control over these representations. I know the leading terms of these are less than the leading terms of the S polynomial that I'm dealing with. So this was the, okay, this was the contents of some of the lemmas I proved. Okay, so now, I will plug this new representation of the S polynomials here, okay? And then I get this. Okay, and then I exchange order of summation. It will be a summation over M. And here the coefficient sums over J and L. Lambda J L. Okay, don't forget the U J L. B J L M. Okay, times GM. Okay, so I have a new linear combination of the GM and what I know the leading term of this. B J L M G M is less than or equal leading term of, I need some more space, I mean, clearly. Okay, I'm be done, okay, very soon. But I shouldn't, okay, I should not rush. So let me move it to the next thing. Have enough time. Okay, let's go slowly. Okay. So why is this? Okay, because I had this. This came out from the canceling lemma. And now if I multiply just with UJL, I mean, this relation is preserved, okay? I have multiplied with UJL. So it comes from here. Okay, also I say this is less than T. Okay, why was that? This is coming from here. Okay, because we have a canceling. Okay, now plug in maybe here. Okay, I show you where I have to plug it in. Here. Okay, now here, the F twiddle is now replaced by this new representation. And then I get a representation where all occurring terms are less than T. Okay, get representation F equals, say, AI prime GI, comma, where all terms occurring on the right are less than T. And this contradicts the minimality. Of T. Okay, so this is the proof. You see, it's not so simple. Okay, it takes time. So there is this canceling lemma, which I did not prove yet. And here you see how it is actually used. Okay. But this is probably, this theorem is, I mean, this is the most important result in the connection with this Gröbner basis theory. I mean, once you have this, you can test. And it also, once you have it, it will be very easy to come up with an algorithm. Okay, I will show that on Thursday. I mean, this Buchberger algorithm is very easy actually once you have this. Okay, are there questions or comments? Because my time is over. Okay, apparently Lev is not here, so nobody asks. Okay, no question. So I will try to compress a little bit this video and then put it online. Okay, and I hope, okay, I can see how many people watch it. So far, there were not so many. I hope many will watch it, but okay, I don't know. Okay, thank you. Then I see you on Thursday. Okay, bye-bye.
Bye-bye.
Bye.
Bye.